Hey everybody, I'm Nick and I'm super excited for today's video. I'm going to be doing a video right now on 12 volt electrical wiring. But what I'm going to do is I'm not really going to take you through the how to wire in this video. I'm going to do that in a video in the next couple weeks. What I want to do today is I want to show you how 12 volt wiring works, how 12 volt electricity works, particularly in the context of automotive applications. There are a lot of good information, a lot of good videos on YouTube, on the internet. There's also a lot of bad information or things that are unclear, or just do this and you don't know why it works. So what I'm really hoping to do today is to show you why it works, and that should give you the ability to figure out what to do when you're putting together something or making a repair on your own project. As a preface, I am not going to go into any kind of depth on AC wiring, house wiring, nothing like that. Do not apply this stuff to house wiring. House wiring is AC at higher voltage and it can shock you, it can kill you. 12 volt DC, pretty much anything on your car, unless we're talking about a hybrid or an electric car, pretty much anything on a conventional internal combustion engine car with no lithium-ion battery is not going to kill you. It is possible that the high voltage coil for your spark plugs could give you a pretty good zap, make your hand numb, your arm numb, whatever. I don't think there's any real danger there. I'm not aware of anyone ever having been seriously injured from a short exposure to a coil like that. But I've definitely been bit by one before, and it's not the most pleasant feeling in the world. So keep that in mind. Additionally, I'm going to be doing some safety overview stuff. I'm going to be talking about fusing and wire size, but I'm going to do that towards the end of the video so that you can understand why it has to be done that way. I'm going to build up to that so that you understand how the different parts of a basic 12 volt system work, and then you can really build up to why we have to do these safety things, what the dangers are, why it has to be done the way that it's done, and how you can figure out where you need to put fuses and what size they're going to be. Okay, 12 volt electrical. Let's start with what is electricity really at its fundamental level. Electricity is the flow of electrons between atoms. An atom, which you can see, I have a little diagram up here. An atom has electrons around it. Different materials have more or less electrons. Different materials have more or less tendency to let their electrons transfer to the next atom and receive an electron from a neighboring atom. Basically, that's how electricity works inside of a wire. Metal is considered extremely conductive. Most metals, that generally means that it loses and gains electrons very easily, and that makes it super useful for things like electronics. Different metals have different tendencies to do this. Copper's very good. Gold is excellent. Silver, I think, is decent. Steel and aluminum are used in wire, but not great. So when you're wiring, this is generally how it works. There are a few basic terms that we'll talk about right now. The electron, that's literally how electricity works. The electron jumps from one atom to the next, to the next, to the next, along the wire, inside the wire, and this is happening on a bazillion atoms constantly to flow electricity. That said, from some stuff I've watched, the actual flow of electrons in the wire, you could run the car all day at high power and the electrons don't actually move notably down the wire. What's happening is at such a small scale that a relatively large flow, a relatively large amount of power doesn't actually move very far. Really interesting stuff. There's tons of other YouTube videos on this stuff, so I'm not going to go into very much more depth on how electronics works at a molecular or atomic level. Moving into really how do we use electricity? What does electricity do for us? There's two main uses of electricity: alternating current, AC, and direct current, DC. And essentially what's happening in an AC setup, this is what conventional house wiring is the electrons are moving back and forth along the wire. The electricity is being pushed out, and pulled back and pushed out and pulled back and pushed out and pulled back many, 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 many times. That number of times would typically be measured in hertz. So you might have a 110 or a 120 volt hertz setup in a conventional house. It's also often referred to as 110 volts or 120 volts. When we get into the realm of AC, things do actually work a little bit differently than they do in DC, and I'm not very well versed in that, so leave your house wiring alone if you don't know what you're doing, and don't take anything from this video to your house wiring. They are not the same. Direct current does not do that push and pull. Direct current, the electrons flow, the electricity flows in one direction along the wire, forming a complete circuit from essentially the positive terminal and the negative terminal through the circuit. And the thing with DC is it has its disadvantages. It's more prone to loss from resistance. Everything has resistance, wire has resistance, and so you're going to lose energy just transporting electricity along a wire. You're going to lose energy. So that's something to keep in mind. When we get into how electronics is practically useful in a car, you know you need wires, you know you need a battery, you know you need an alternator to continue producing electricity, you know you need a positive and a negative, you know you're probably going to need fuses. You kind of know what some of these parts are, but what do you do with them? There are a few things we can look at how electricity works that can help to understand why we're doing what we're doing. There's the idea of voltage. Now, voltage in a DC electrical system is best described as pressure in a hydraulic system. For example, if you were to turn on the garden hose doesn't just have water coming out of it. If you put your thumb over it, there's pressure pushing water past your thumb, right? So the more pressure you have, the more water is going to get past your thumb. The more water is going to overcome the resistance of your thumb, right? It's very similar in electronics. If you have 9 volts, that may not be able to overcome the resistance of your starter motor. However, if you have 12 volts, that's a significant increase in energy, and it will be much better able to overcome the starter motor, turn the motor, start your car. That starter motor is just one example. There's tons of examples of automotive electronics that don't play well at lower voltages when the battery's close to dead, and it can actually cause all kinds of problems with a computer-operated EFI type setup. So voltage is something that's fairly important. Typically, you want to see a battery in an automotive application at 12 volts when the car's off, and at 13.5 to 14.2-ish volts when the car is running. The reason for having a higher voltage is essentially that the higher voltage being a bit above the battery keeps the battery charged, pushes that energy into the battery so that the battery is always full when the car is running. After voltage, the next item that we need to consider is current. Current is the volume of flow through the wires, through a circuit. So current could be thought of as, if you turn on the garden hose, how much water comes out of it. You might have 1 gallon per minute, or 5 gallons per minute, or 40 gallons per minute. Now you put your thumb over the end of the hose and you restrict it, you're putting resistance on it. It's going to shoot out further. It's doing work. It's shooting out further. It's changing it, but it's not going to flow as much. Your thumb actually provides enough resistance that it slows the flow down. So you have pressure, voltage, you have current. Current is typically measured in amps. There's a very wide range at which an item in your car might use a different number of amps. Something like an electric fan or a fuel pump could use 10 or 15 amps. A performance electric fan in a race car might use close to 30 amps. A relay maybe draws half an amp to maintain on. Little LEDs can run well under 1 amp. Headlights can run 5, 10, 50, It just depends on what type of headlights you have. There's a very wide range of amperages, so you need to do some reading when you're coming up with a circuit or repairing a circuit and make sure that your wire is heavy enough and your fuses are heavy enough and everything is heavy enough to support the amperage that is going to be flowing through that circuit. Additionally, you have wattage. Now, remember I said you put your thumb over the end of the garden hose and now it does work. It shoots further and it shoots a stream, and you can actually use that to clean something or to shoot water out over your lawn or whatever. Well, that's work. And so what you can think of is work is pressure times flow. So you put your thumb over the garden hose and your garden hose is set to 50 psi. Depending on where you live, it can range anywhere from 50 to like 150 psi. 100 psi is, my understanding, is pretty typical for city water systems. So you put your thumb over the hose, and if it's regulated to 50 psi, it'll go a ways. Now, if you had the ability to increase that regulator to 100 psi, that's a lot further that stream's going to go, even if not very much more water flows out because your thumb is still restricting it. It's going to go a lot further. It has a lot more pressure behind it. If you increase it further to 150 psi, you're going to see additional gain. That's voltage. Now, let's say that you are trying to run a sprinkler. Well, with a sprinkler, if it's an automated sprinkler that moves back and forth, the type you'd see Grandma put out on her lawn, right? It just rolls back and forth. If you just barely crack the water, you've got low, maybe medium pressure, low pressure, and low flow. The sprinkler may not even have enough pressure or flow to do that. Now, if you have full flow to your sprinkler, if you have full pressure to your sprinkler, say 50 psi, and you're running 10 gallons per minute through that garden hose, that's probably plenty of volume to move the sprinkler. It might not move super fast, but it will move. If you're running a setup that's flowing 40 gallons per minute, the sprinkler is going to move a lot faster. It has a lot more volume pushing through it. It's going to go further. It's also going to create more pressure because the restriction of the sprinkler is going to increase the pressure. It's similar in electricity. In electricity, you don't tend to see a restriction do very much to increase voltage. Typically, your power supply, your alternator, your battery are not capable of producing more pressure than what they run at all the time. Your alternator will be regulated so that it never exceeds a reasonable pressure of something like 14 volts. And your battery is got 12 volts at its best, and the more that you're drawing from the battery, the less it's going to be unless the alternator is saving it. So you're not really going to see that increase in pressure in a electrical setup, in a 12 volt DC electrical setup, but you will see a difference in the flow. If you have less flow, you're going to have less water coming out of the hose. It's not going to go as far. You're doing less work. The formula to calculate that work with anything, whether it's a light bulb, whether it's a fan, whether it's running your fuel pump, is voltage times amperage equals the amount of work done. It's your watts. Pressure times current equals work done. So that actually works very straightforward. 12 volts times 5 amps equals the number of watts. When you're thinking about electricity and voltage, when you get into more complicated stuff, it's important to consider the way that this pressure works. It is possible to have 14 volts on one side of an item and 12 volts on the other side of an item, and it will still work because there's flow across the item. However, it's also possible that it will not work as it's intended because there's too much voltage on one side of it. The flow across it is not great enough. You're looking at essentially a pressure difference. If you blow up a balloon, right, there's a little ambient pressure in the air, but it's not really noticeable. But you blow up a balloon and you have, say, 40 psi in the balloon. That's pressure, and if you let go of the balloon, it'll shoot away and it will just empty because there's more pressure in the balloon than in the ambient air. Now, if you take that same balloon, you blow up two balloons. You blow one up to 40 psi and you blow one up to 15 psi. It's small. And you put them together. there's still going to be a flow from the more pressure to the low pressure balloon if you connect them with a straw or something. But the low pressure balloon is not going to receive air nearly as quickly as the balloon emptied itself into the air. It's because there's pressure there. The difference in flow is going to make less work happen. When we're looking at a circuit, there are a few basic components that we need to know about. One is your power source, right? You're going to have a battery. And your battery is going to be what the main supply of power is for the vehicle. The battery does two things. It supplies power, and it also kind of acts as a reserve. Sometimes, whether it's just turning a new item on or off, your headlights, your brake lights, the radiator fan, whatever it is, or whether it's just running along, the battery acts as a kind of buffer for the electrical system. It is a reservoir. You have a sudden increase in draw. The alternator may not be snappy in producing that extra energy. The battery will have it. The battery just kind of smooths things out, keeps your voltage more consistent. The battery is a super vital part of your electrical system. There have been cases where a battery's been disconnected and a vehicle continues to run because the alternator is producing enough energy, but typically those aren't stable and they won't run reliably. You can't typically run a car with no battery. So when we're looking at any electrical circuit, the battery is kind of the start and the end of it. You have the positive terminal and the negative terminal. And what makes the whole thing work is that there is a difference in potential or a difference in pressure between the two terminals. The total difference adds up in a typical 12-volt system. It adds up to 12 volts. You have wires in your system. You'll have the load. You'll have the item that is going to perform work. In this example, I've shown a light bulb. It's possible that this could be a radiator fan, a fuel pump, a fuel injector, your horn. There's tons of things that this could be. I'm just using a light bulb as an easy example. So you have these components. Typically, you don't want these things running 100% of the time. You don't want to go out and take your battery off. So almost always there's a switch of some type involved in the system. The switch opens and closes, opens and closes. And so when you have a complete circuit set up, there's a complete flow of electricity all the way from one end of the battery to the other. You have a complete circuit. And when the circuit is closed, it would turn on the bulb. It would activate the circuit. It would turn your horn on, your radiator fan on, whatever it is. Now, technically, electrons flow from the negative terminal of the battery through the circuit to the positive terminal of the battery. That's technical fact. There's a bunch of complicated math on whether current flows the other way, on how AC works, DC works. I don't know, don't want to know, don't need to get into any of that. I've drawn my diagrams with electricity flowing from negative to positive. If you don't like it, make your own video. I appreciate it. You can see the switch is open and the switch is closed. Turns the light on. When the switch is closed like this, we would refer to this circuit as a closed circuit. The circuit is on, the circuit is closed. When the switch is open like this, we would refer to it as an open circuit, or the circuit is open somewhere, right? And what that means is that the circuit's not complete. It's not flowing, it's not active, because there's somewhere where there's a break in the electricity. In this case, it's an intentional switch. We would also call a circuit open if, say, a wire was worn where it goes through a firewall or where it passes a bulkhead or something like that. The wire could be damaged, physically damaged, could be melted, could have overheated, could have melted the lead at the battery terminal. Tons and tons of things that can happen like that. That's why you need to take care when you're wiring. We would refer to that as an open circuit. Pretty much that's best case scenario. Oh, the circuit, something physical damage wore or melted or something, and the circuit's open. It's best case scenario from a safety standpoint because it means that it didn't start a fire. When the circuit's closed, electricity is allowed to flow. This is the fundamentals of how a circuit works. Electricity is flowing all the way around the circuit, through the load, performing work in the load, and back to the battery. I want to talk about grounds for just a minute, and I'm going to go back to home wiring. Don't take this video and the information to home wiring. Home wiring operates at higher voltage, can start a fire, can shock you. The AC is much more dangerous than DC. The higher voltage will jump and arc to your body much more easily, and AC can kill you because it's going to disrupt back and forth the electrons in your body. Water's conductive. We're made up of mostly water and salt. That makes us very conductive, relatively. And AC, bad news. Don't mess with it unless you know what you're doing. 12 volts, it's less dangerous. There's still fire hazards. Stuff can overheat. Wires can overheat. Loads, light bulbs, whatever it is, if it's not properly set up, your ground stuff can overheat, and it's a problem. Make sure that it's set up right. So you'll see this symbol, or a symbol very similar to this, used to describe grounds on a lot of electrical diagrams. You'll see it all over the diagram. It's not like stuff just goes all the way back to the battery. In a lot of diagrams, it goes to a ground. You have a positive source, and then it goes to a ground. And that's a way of making the diagram actually a lot easier to read. And what ground is a little different in home wiring and automotive wiring. In home wiring, you would consider the ground literally like the earth, like the ground. And that would be considered an infinite sink. It can accept a near infinite amount of energy as long as the wire can accept that much energy and deliver it there. That's not really how a ground is described in automotive stuff. There are some features that are kind of along that line of thinking, but what I want you to think of ground is the ground is the chassis of the car. Typically, on the vast majority of automobiles, the negative terminal of the battery goes to the chassis of the car. And the entire chassis of the car, the metal, the body, the frame, is connected to the negative terminal of the battery. What this does is it lets you use the chassis of the car as a gigantic wire, so you don't have to run a ground wire all the way to the back of the car. You don't have to run a negative wire all the way to the back of the car. That has a lot of convenient things to it, but it also opens up a lot of potential failures if you don't have good connections between all your different body panels on the car and the frame and the battery. There's a lot of potential for failure there, but it makes a lot of convenient things because you don't need to run a separate wire all the way back to your taillights, all the way back to your fuel pump, all the way back everywhere. You can conveniently ground much closer to the body of the car. So I've come up with this modified diagram of our simple circuit here, and you can see in this diagram electricity flows from the battery to ground, to the chassis of the car, the frame of the car. And then, to complete this circuit, rather than running this wire all the way back to ground, all the way back to the battery, it's simply run to ground. It can be close to it. This could be, for instance, a taillight at the back of the car. When the battery is at the front of the car, you have a short wire that goes to ground at the front of the car. And then at the back of the car, you've got a short wire that goes to your battery. For the sake of simplicity, I maintain the position of this switch. This switch could very easily be in the positive side of the circuit. In fact, that's probably more common to find it in the positive side of the circuit. But this is a very typical way that you would see grounds used. You might see it drawn like this, or something more similar to this, where the grounds, they're not close together. They're not obviously connected, but because you know it's the ground, you know, okay, it's essentially functioning as the negative terminal of the battery. The negative terminal goes back to the battery. The negative terminal goes to ground. The ground goes back to the battery through the chassis. You know that that's the negative terminal of the battery. You know that that's going to be a completed circuit between ground and your positive source, whether you're getting that directly at the battery or at a positive bus bar that's been ran to closer to wherever you're working. You know that you have a complete circuit there. So we've established what a ground is. We've established how electricity flows. We've talked about what a switch is. But let's say you have a more complicated situation. Maybe you are running halogen headlights. Maybe they draw 15 or 20 amps per headlight. That's relatively a lot of energy. Now you've got a couple different options. You could run that energy all the way into the cabin of the car, run it through your headlight switch, run it back through the firewall a second time, run it way up to your headlights, give it to your headlights, and then go to ground. That's a lot of wire travel for a relatively lot of energy. The wire adds resistance, so you need a bigger wire to safely travel all that energy, all that distance. The wire's going to have a voltage drop, so your headlights aren't going to be as bright as they potentially could be. And you're running an increased fire risk because you pretty much have to run the positive power into the car and then back out of the car. You're making 2 unnecessary trips to the firewall. So as a solution to that, there's something called a relay. What a relay is an electronically activated switch, essentially. I'm not going to get into more complicated 5-pin, 6-pin, 50-pin, bazillion pin relays, solid state relays versus conventional relays. I'm just going to talk about conventional relays right now. A conventional relay has an electromagnet in it, and that electromagnet turns on and off, and it works against a spring-loaded switch. Typically, when the electromagnet is off, the switch is open, and when the electromagnet is on, the switch is closed. You can see that here. This coil here is our electromagnet, and this is our switch. Now, you might be going, well, this seems like it's going to really complicate things. And it does, but it's an extremely necessary part of car electronics. You don't want to run all of the power for your car audio system up to a massive switch in the dash, turn it on and off when you're running, say, 1,000 watts RMS. You're running 100 amps through that switch, almost 100 amps through that switch. That's way too much. That's a ton of energy. You need a huge wire. You need a massive switch with big contacts in it so they don't get hot and burn up. So there's just big problems with running that much energy through a switch. That's why you use a relay. You use something remote. It doesn't have to be in the dash of the car. The relay can be a little bit bigger box that has larger contacts in it to safely transfer that energy. It's set up for it. This diagram is kind of a simple example of how a relay could be used. In this example, the relay is switching the ground side. It's not switching the positive side, but it works the same either way. The battery's grounded, so from any point on your chassis, you can ground. And grounding, we have a switch. Let's call this the brake light switch on the gas pedal. The switch turns the relay on. The relay gets its positive from the battery. The switch turns the relay on. When the relay is turned on, the relay closes and completes the circuit for the brake lights. That turns the brake lights on. Now this switch could be the headlight switch. If you have manual headlights in a classic car or in a race car in a performance application, it could be the headlight switch. You turn the headlights on, the relay closes. The relay could be out under the dash or under the hood somewhere, or under the dash, but probably under the hood somewhere close to the headlights, so that you're not running all of this power wire into the car and back out of the car all over the place. And so let's kind of look at that example. I've kind of modified the circuit just a little bit. Functionally, it's the same, but I've added the firewall. Now, you could, like we said, run that was nice. Okay, continuing. You could, like we said, run all of this positive power all the way into the car, run it through the firewall, run it to a switch, run it back out of the car to the headlight, run the headlight to ground. Or you could run it to the headlight, run the ground all the way inside the car, have a switch, run to ground. Couple ways you could do it, but now you're running all of your headlight energy all the way into the car. It's going to be several feet of wire for that. Or you could have your positive go pretty much directly to the headlight. That could be a fairly short run in most cases. Even if it's going to the other headlight, it's not that long of a run. And then you can use a relay that's mounted close to the headlight or on the firewall or somewhere that's convenient to service. You can have that relay activate the headlight. This would need to be something hefty, 12 gauge, 10 gauge, something like that, depending on how much load your headlight's going to put. And then you could run a little tiny 14 gauge through the firewall into the car. Now this saves you from having to run anything through the firewall twice. It saves you from having to run a bigger wire into the firewall. It saves you from having more fire risk inside the cabin of the car because you're running more amperage through the firewall. You're running a little wire, can have a smaller fuse, relay doesn't draw very much power like the headlights do. Lots of advantages to having the headlights be remotely switched. And additionally, that switch doesn't need to handle a big load. The relay is going to draw maybe half an amp. High resistance, low load, half an amp. That headlight might draw 20 amps, depending on if it's like a conventional halogen, what it is. That's a lot of load to put on the contacts of a switch that you're going to be turning on and off every time you drive the car or every other time you drive the car. So that's going to burn up the contacts in the switch. It won't last forever. The same switch will last almost forever running that relay. Now, I put another example here because I want you to see that this can get a little bit more complicated, but the foundation is honestly all the same. The battery's grounded. From your ground, the ECU gets its ground, it gets its power. The positive also goes to the ECU, supplies the ECU with its own complete circuit. Now, this is an example that's obviously just for fuel injection. You could look at this similar things like an MSD box or a capacitive discharge box, something like that on a carbureted application. Anything like that. You could have this for your ignition switch could be the ECU in this case, and that could turn on your fuel pump if you have a fuel pump, even if you're running an electric fuel pump, even in a carbureted application. There are tons of things. I wanted you to see that this can be more complicated. You don't have to have a literal physical switch that controls absolutely everything. You would have a switch somewhere, probably in this 12 volt, that would tell the ECU, hey, turn on, hey, turn off. But for the sake of this, I really just want you to understand what's going on here. And the ECU gets its power, the ECU is fully powered, and the ECU has the ability to turn this ground to the fuel injector on and off. So the fuel injector has positive all the time, and the ECU has the ability to turn this ground to the fuel injector on and off a bazillion times a second, and that meters fuel into the engine. This fuel injector could be one of any number of things. It could be a fuel pump instead. The ECU could trigger the fuel pump. It'd probably do so through a relay, but it could trigger the fuel pump. It could trigger your brake lights. It could trigger a nitrous oxide relay. It could trigger all kinds of stuff, a line lock, launch control, anything. It doesn't have to be a injector. Typically, most ECU switched items are ground switch. They get positive all the time, and the ECU turns the ground side, the negative side to them, on and off. It's not exclusively the case, but that's pretty typical, so that's something to consider. All right, so having looked at how the basic parts of a circuit really work, talked a little bit about voltage, current, watts, flow, all of these things, I want to get into a few more specifics on what you might be interested in when you're working on something. Voltage. We said it's the pressure difference between the negative and positive terminal of the battery. We said it's the pressure of the system, it's the flow. It is the pressure difference between the negative terminal and the positive terminal of the battery. In a 12 volt system, that difference should be 12 volts. If you put a light bulb in the middle of it, the light bulb sees, basically, the light bulb is going to see 6 volts of draw from the negative and 6 volts of supply from the positive, and it's a 12 volt circuit. Now let's say you put 2 light bulbs in the middle of it. Depending on the resistance value of the light bulb, and it's math, I'm not going to get complicated into it. There's a bazillion different types and sizes of light bulbs. I'm just going to diagram this a little bit for you. If you have 2 light bulbs in the circuit, the first light bulb from the negative terminal to the light bulb, it sees a push of 6 volts. To the next light bulb, it only sees a pull maybe of 4 volts, 5 volts, depending on how much that light bulb is restricting flow, how much that other light bulb's in the way. It doesn't see the full value. Now moving to the second light bulb, that second light bulb has the same thing. From the positive, it's got a direct connection. From the positive, it sees a full draw of 6 volts. It's trying to take 6 volts from it, but that other light bulb isn't bringing 6 volts its way. That other light bulb is in the way, and it's going to drop voltage. It might only see 4 or 5 volts or whatever. So when you put things in each other's way like that, when you put things in effectively in series, you can create this problem where there's not enough draw. Now, it is possible to have this work. You would still have both light bulbs probably light up, but they're going to be dimmer. They're going to be running with significantly less energy through them because there's not good supply on both sides of both bulbs. You've created an increased resistance in the entire circuit. However, if you were to run these light bulbs not through each other, but in parallel with each other, the wire goes to one light bulb and it goes to the other, and on the other side the wire goes to one light bulb and it goes to the other. In parallel, that light bulbs, they both get full juice. They're not really aware of each other's existence. If we're going to personify them a little bit like this, they're not aware of each other's resistance. They're not in each other's way in terms of the flow of electricity. A short circuit. So a short circuit is typically described as positive going directly to negative, positive going directly to ground, then positive terminal going directly to the battery. It's typically how you describe it. What a short circuit really is, or what makes it dangerous, is when there's not enough resistance in a circuit to slow the flow of electricity. So you could have a big bright light bulb, very low resistance, flows a relatively lot of energy through it, but you're feeding it with tiny little wires. You're feeding it with like 16 gauge wires, and it's going to draw 15 amps. Those 16 gauge wires, 4 feet long each, they might only be able to handle like 4 amps. So what's going to happen is those wires, there's too much energy flowing through them. They have a resistance value. Even though it's very low, they have a resistance value. There's too much energy flowing through them. They're going to get hot from being overused. Now, the light bulb may light up for a moment. It may even light up bright for a moment, but as those wires get hotter, it's going to get dimmer, and eventually this is where you create a fire risk. So you have to make sure you're using the correct size wire for the load, for the amount of current that's going to flow through your light bulb, through your blower motor, through your radiator fan, through your fuel pump, through whatever it is. You have to have good enough wire. Also, you have to have protection so that your positive can't go straight to ground. If the positive and the negative get directly in contact with each other, it creates a short, and that short is going to get hot. The wires get hot. Even if you have a big wire, if it goes straight to ground with no resistance at all, there's going to be probably a fire, because the battery's going to say infinite current, no restriction. We sent all the energy there. That's a problem. It's actually a huge problem, and that's how car fires happen. That's how electrical fires happen. So that's super important to watch out for. Now, I keep talking about resistance. I want to talk a little bit more about what it really is in a tangible way. Resistance is literally the resistance to flow. It's a restriction in the flow. More pressure can help overcome resistance, but you'll see more flow with more pressure, but it's not typically linear. Just like increasing the pressure in a garden hose, if you go from 50 to 100 psi, you're probably not going to double your flow when you have your thumb over the end of it, but you will see more work done. This is kind of the same way. You'll have more flow, you'll see a lot more work done, you'll have a little bit more flow, but it's not linear. Now, resistance is stack, so we put those two light bulbs in series, right? Resistance is stack. So if we had a 1 ohm light bulb and a 1 ohm light bulb, and we put them both in a circuit, now we have 2 ohms of resistance in the circuit. That's one way that you can calculate kind of how much resistance is in the circuit. You can figure out if that's going to be a problem with voltage drop. There's some fancy math. I'm not going to get into it. There's tons of calculators online. That's beyond the scope of this video. Now, interestingly, when you put resistances in parallel, they don't drop the same way. You don't subtract them or do a simple divide. You have to do some fractional math. Get the fractions all happy with each other so you can add them up. And then you take the bottom number of the end result of the fraction and get it back to where it's 1 over that number, and that's your resistance value. It's kind of complicated math, but the reason that this could be important is you might have something like a fuel injector driver that requires a certain amount of resistance. The ECU may only be able to put a certain amount of energy on that ground for those fuel injectors. Now, if you're running high impedance injectors, is what they're typically called, they have a high resistance value in series or in parallel, depending on if you're running batch fire or if you're running sequential. There's all kinds of stuff like this. I'm just using this as an example. These may have to have a high resistance value, or too much energy will flow through and burn up your ECU. So if you have a circuit where something is supposed to be in series, you can't necessarily just make it in parallel. You're going to flow a lot more electricity because they're not slowing the electricity down as much. The electricity more or less gets here and it says, oh, I have 3 separate paths. I can flow a ton of electricity through all this. Versus in the series example, you have significantly less flow of electricity because all of these are creating a resistance. Now, resistance is measured in ohms. That's how you're going to see it standardized in ohms or kilo ohms or milliohms or some form of ohms, bigger or smaller. That's how you're always going to see it characterized in electrical diagrams. Current, we talked about it, but it is still the volume of flow through the circuit. Current's measured in amperage. Pretty basic. More pressure will flow more amperage, but it's not linear. You're not going to see doubling your voltage is not going to double the amperage through a circuit typically. Current is what makes stuff hot. When you have too much flow through a circuit, too much flow for your wire size, too much flow for the component that you're using, whatever it is, it's going to get hot. So if you have a LED, a little light bulb for your dash, and it's not meant to work with 12 volts, it might need more resistance than it can create by itself. You'll burn that LED out. That probably won't start a fire, but it could. You'll burn that LED out, or that light bulb out, or that switch out, or whatever it is, because you have too much current flowing through it. Current is what makes stuff hot. Watts, we talked a little bit about it. I said that's the work being done when you put your thumb over the end of a garden hose. Watts is the work being done. So you can say current times pressure, current amperage times voltage equals the work done, equals the watts. So 30 amps at 12 volts is 360 watts. That's relatively a lot. 30 amps would be a very heavy duty, like cooling fan or something, a very heavy duty fuel pump for a high horsepower application. That's relatively a lot for a automotive application. That'd be a very bright headlight. But so you'll see a 60 watt bulb then does more work. You would expect it to be brighter than a 30 watt bulb. So a lot of times when you're comparing different components, whether it's radiator fans or light bulbs or fuel pumps, you can get an idea of which one is going to perform better by how many watts it says it's going to draw. Or how many amps it says it's going to draw, because we're pretty much working right in the 12 to 14 volt range, and that side of the math is very, very stable in 12 volt DC system. So a lack of voltage, though, can prevent this from working. If you have a light bulb, say it's a 30 amp light bulb, and you provide 6 volts to it, but it's intended to work at 12 volts, there's not enough pressure. You know, it might still draw 30 amps, but there's no pressure. There's no work being done. It probably won't be able to draw 30 amps. Remember how there's that curve. It's not linear, but there's that curve in terms of how voltage affects flow. It's not going to draw the full 30 amps most likely, and it's not going to be bright. Now, if you have over voltage, it'll be brighter than advertised, but that extra flow going through will shorten its life. So if it's supposed to run at 12 to 14 volts and your alternator's freaking out and you're running 16 or 18 volts, stop, because that's really bad. But that can happen if you have a regulator fail. But if you're running 16 volts through a bulb that's intended to run at 12 or 14 volts, that bulb is going to be super bright. It's going to be a lot brighter than normal. It has more flow going through it. It's got lots of pressure to really make bright light, but it's going to burn out faster. It's not meant to handle that increased flow, that increased voltage, that increased pressure. That's not what it was built for. It wasn't intended to last as long under those conditions, so you're not going to see that be an effective long-term use. Finally, I want to get to fuses. This is the most important part of the video, fusing. Fuses protect the circuit from starting fires. We talked about this with the shorts. If too much energy flows through a wire, and the wire's not big enough, the wire gets hot. The wire can light its insulation on fire. In rare cases, the wire could light the actual metal on fire. It can light the paint on the fender that it's running along or whatever on fire. It can light your carpet on fire. If the wire's under your carpet, behind your headliner, inside your door panel, wherever it is, that wire can get hot and it can start a fire. And I mean, they can get hundreds of degrees. I have been burned by hot electrical wiring, and I've never had one that started a fire. It can be so hot that it can very easily light the underpadding of your carpet, or the foam behind your headliner, or the foam in your doors, or the paint on your fender, or whatever on fire. Huge, huge, huge fire risk when you're talking about electricity. That's why you need to make sure you're running the right size wire. There's a bunch of charts online, and I'll link one in the description. You need to make sure that for the load that you're running at the length of wire that you're running. The load and the length of wire determine the size wire that you need. You might get away with a 10 amp load on a 14 gauge wire if it's a 4-foot length of wire, total length of wire in the circuit, but you might need a 10 gauge for the same load, 10 amps, if it's a 15-foot circuit, total of 15 feet of wire in the circuit. Another reason to use relays, saves you wire. In the event that something blows, in the event that a transistor melts in your MSD box, or your capacitive discharge box, or something in your ECU goes bad, or whatever it is, and these kind of failures can happen from any brand. It's not exclusive to any one brand, but in the event that something like this does happen, you might end up with a short inside that component. Less resistance means the wires are going to flow more. Even if the circuit's not functioning properly or not doing what you're intending it to do, it's going to flow a lot more volume, and that's a bad thing. So you need to make sure that you are well fused. If a circuit is supposed to flow 10 amps, you should probably have a 10 amp fuse, even if the wire's good for 15 amps. If your circuit is supposed to draw more than that and your wire's too small, you just can't do it. You need to upgrade your wire. You need to have bigger wire. Don't do it. The fuse needs to be the same size as the maximum safe current for the wire, or it can be smaller than that. You might run a 14 gauge wire because that's what's convenient to use, to something that only draws 2 amps. Well, you don't need a 10 amp fuse, even if the wire is capable of supporting that. You'd be best served to run like a 3 amp or a 5 amp fuse, something that's a little bit bigger than what the component will run, in case it has a higher draw when it's first starting or something like that. But you don't want to run a bigger fuse. You want that fuse to blow as soon as that component exceeds its operating parameters. Fuses are typically placed on the positive side of a circuit. They don't necessarily have to be. They function the same on the positive and the negative side of a circuit. With the convention of using chassis ground, that would massively complicate fusing every circuit before it goes to chassis ground. For the sake of convenience, typically positive from the battery terminal is run to a fuse panel or fuse box. It's a big power wire, and from there it's fused and broken off to a bunch of smaller circuits. The hot supply, the power supply, the positive supply, to a bunch of smaller circuits. The thing is, that fuse should be as close to the battery as possible. In the event of a short on that positive wire from the battery, you have a car accident, that wire gets crunched. If there was no fuse close to the battery, that wire is no good. So while I'm doing a build, I always put a fuse as close to the battery as is reasonably possible, have the shortest possible amount of battery cable between the battery and the fuse. And then additionally, every time you go to like a bus bar and you step down in size, you have to fuse again. I'm going to show you that right now. I took our headlamp tail light relay model and I added some fuses to it so that you can see what I'm talking about. Let's say that we ran a 10 gauge wire directly to the battery to power these relayed headlights. Well, those headlights, let's just say that together they're going to draw 25 amps. I'm going to fuse them at 30 amps. I only put one headlight in the circuit, but this would probably have headlights in parallel with each other. It would work essentially the same way. So 25 amp circuit, I'm going to use a 30 amp fuse. Go one size up. It's going to be plenty of fuse for the circuit. And then I'm going to put that fuse as close to the battery as possible. If I put that fuse up here close to the headlight and the wire gets chafed or crimped in an accident or anything down here, the wire still gets hot. The fuse did no good because the fuse never sees the problem. If you put the fuse close to the battery, it's going to be before the problem, between the problem and the battery, and it's much, much more likely to blow. So this 10 gauge, I made this wire thick. This 10 gauge, at some point for this relay, for the sake of convenience, we want to send it to our relay, make it a smaller wire. That's great, but the problem with that is that relay doesn't need 25 amps of juice. If the wire gets crimped here, you know, and we have a 30 amp fuse over here, the wire gets crimped here, it takes 30 amps to flow through a much smaller wire and through that relay, through the coil side of that relay, before that fuse blows. That's not good. That increases your fire risk. This might be a 10 gauge wire, and this might be like a 14 or a 16 gauge wire, or smaller if it's an OEM type application. Sometimes they use like 18 gauge tiny wires, and you don't want to be running a big load through that. I would probably put a 5 amp fuse in there, just because 3 amp fuses are harder to find. 5 amps is plenty small enough that it's going to blow like that in the event of a short. If you can find a 3 amp fuse, the relay only needs a 3 amp fuse. Most relays draw less than an amp, something like a half an amp, to activate them while they're running. So by fusing the positive side close to the battery, you can keep the circuit very, very clean. It would be a lot messier to add a fuse here and to add a fuse here. It'd just be a lot messier to have fuses all over the car. Ideally, you keep them close together, keep everything well fused, keep everything very safe. Hey everybody, I know this has been a super long video. It actually turned out quite a bit longer than I thought it was going to. I hope this has given you a really good primer for how to do 12 volt electricity, how it works, what to watch for. I'm going to be doing a couple more follow-up videos on this in the next couple weeks. I'm going to do a video where I show you what some good wiring practices are and aren't. I'm going to show you how I did them on my car. I'm going to show you what kind of crimp to use, what kind of butt connector to use, when I think you should use solder, when you shouldn't, why I prefer butt connectors most of the time to solder, and how much easier they tend to be than soldering every single joint. I'm going to be doing a video on how to use a multimeter, how to use a meter to check for voltage, to check for alternator charging, to check for battery, to check and make sure that you have good grounds everywhere. I'm going to be showing you a video on that. Let me know what other types of videos you'd like to see. Let me know what topics you want me to go in depth with. Let me know if there's any points in this video you'd like me to clarify. If you leave me a comment, I'll do my best to answer every comment and answer any questions that you might have. I'm a small YouTuber, so if you enjoyed this video, if it helped you, please give me a subscribe, like and subscribe. I am trying to grow. I want to continue to do educational content, and I want to make it easier for you to get into the automotive hobby and fix your own car, save money, and just enjoy driving. Thanks for watching. See you next time.